In this video, we will solve for electric field of charged spherical shell using Gauss law. As shown in this slide, we will find that the electric field outside the charged shell is very similar to point charge. But inside the charged spherical shell, the electric field is zero. So let us begin. Before we do it in proper way, which is using Gauss law, we like to at least attempt a derivation by qualitative means. And one should always do that way, because with little investment, we can get much more insight. In this slide, we make the charged spherical shell very small, and it looks more like a point charge. Therefore, we can use Coulomb law, which is force being proportional to product of the charges and inversely proportional to square of the distance between them. We consider one charge as test charge, so that electric field is force divided by the test charge, which will give electrical field as this. And this happens to be the correct relation. However, we will prove later in a proper way using the Gauss law. Now we will continue our qualitative assessment for electric field inside the charged spherical shell. Let's say we like to find the electric field at the point P. We divide into two sides, below the P, which is green, and above the P, which is blue. To be precise, below and above is defined by the chord, or rather a disk, because it is spherical shell, in such a way that P lies in the center. One side is considered below as green and the other side above is blue. We can assume the charged spherical shell to be made up of many tiny point charges in the spherical shell. We see that for every point from the blue region has a corresponding point in the green region which will have electrical field in opposite direction. However, the electric field from the point charges in blue region is weaker than that of the green region because it is much further. We know that electrical field from the point charge goes over 1 over r square. On the other hand, there is more blue region than green region, giving more electric field from blue region. So it is quite possible that the electric field from blue region may be equal to electric field in the green region, which is in opposite direction, and the net may contribute to zero. This is good enough qualitative justification, but let me build a better case for the last point. Solid angle from P to the blue region is equal to solid angle to the green region in opposite direction. Therefore, the area due to solid angle is proportional to r square, which just compensates the weakness of electric field due to distance. You can ponder over these points later, but let's proceed and use Gauss law to calculate the electric field. Let me briefly describe the Gauss law before we apply to the problem. It is mathematically written in this integral form. It is also written in differential form in this way. The differential form is one of the most elegant equations in physics. However, we will focus on the integral form. Let us see how these notations are defined. Gaussian surface, as shown on the right, is any hypothetical closed surface that contains the charge, which we call here as Q inside. It could be one discrete charge, many discrete charges, or charge distribution. In each case, we are only interested in charge inside the Gaussian surface. Let us look at the left-hand side of the equation. The integration with a circle on it means integration or summation that is carried over the hypothetical Gaussian closed surface. ds vector is the surface area vector, which is small surface ds on the Gaussian surface times the unit vector normal to that small surface area. Dot product of EDS is the electric flux coming out of the small surface. It is component of E in the normal direction times the small surface area. Now let us use this to calculate the electrical field. Let us now solve for the electric field outside of charged shell. For this, we create a Gaussian surface as spherical shell enclosing the charged spherical shell with the same center. The radius of the Gaussian sphere is larger than the charged shell. The reason for choosing this Gaussian surface is that electric field along the radius will be same at all points of the Gaussian surface due to rotation symmetry. So we can take E out of the integration and have integration only over the surface area, which is 4 pi r square. From here, it is simple and we can solve it as this, which is similar to Coulomb law. To calculate electric field inside the charged shell, we follow the same procedure, except Gaussian surface has radius smaller than charged spherical shell. There is no charge inside this Gaussian surface, so the right hand side is 0 and we get electric field inside the charged spherical shell as 0. Let us now summarize in one slide. This is the summary. We write the electric field as given on the right. It tells that beyond R, the electric field in radial direction is similar to Coulomb law. The Coulomb's law represents the force and contained product of two charges. So we divide by the test charge. This will give electric field which contain one charge Q. The electric field is due to this charge. Inside the charge shell, the electric field is 0. The graph below help you visualize the electric field. It is 0 till the radius of shell. After that, there is a sudden discontinuous jump and then slowly decreases as 1 over r square. I hope you have enjoyed this video. Bye bye.